Now we'll discuss some more applications of the operational amplifier. The first application is the voltage to current converter, which is also called as voltage controlled current source. Okay, because the input is a voltage and the output will be a current. Now there are two types of V2I converters, namely one with a floating load and one with a grounded load. Let me tell you the meaning of a floating load. A load is generally connected like this, a resistance here from some terminal T to the ground. Now in this circuit, if you observe, there is no ground. The load is connected between two terminals. So this is a case where you call it a floating load, where there is no ground. Okay, so let us analyze this same procedure as we have done till now. The terminal voltages VA, VB will be equal to 0, and the II, this current II will be equal to IL, and this is all equal to 0 minus this loop. Okay, 0 minus VI by R1. So from this you can write IL is proportional to VI. That means current is varying with respect to voltage. So this is our V2I converter. Next, let us take a grounded load now. This is our normal grounded load, which is connected to the ground, normal load. Okay, here from this node we can write II plus I is equal to IL. Okay, now if you substitute II is equal to this and I is equal to this from the equation. Now remember how we got this 2V1. Let me tell you how we got this 2V1. This is, if you see, nothing but a non-inverting amplifier. So for a non-inverting amplifier, what is V0? 1 plus RF by R1 into V1, right? Here RF is equal to R1. So what do you get? 2V1. Okay. So this is how we got V1. So coming back to this equation, now if you put the values, you will get this. Finally, you will get IL is proportional to VI. So it's the same result. So this is also a voltage to current converter. Now let us go to the other thing, which is a current to voltage converter. Sorry about this, current to voltage converter. Okay. Now this is also called a current controlled voltage source. The earlier one was a voltage controlled current source. Okay. Now see the diagram. Same thing, VA is equal to VB is equal to 0, and II value, this is II now. This is nothing but V0, this is V0 in this loop now. Okay, V0 minus 0, this is the VA 0, okay, by R. So what do you get? V0 proportional to II. So we have shown that output voltage proportional to input current. So this is a V2I converter. Very simple circuit. Next, let us analyze an integrator. So you must have heard about this. This integrator is nothing but a circuit which performs integration operation. And before we start the integrator, just recall that current in a capacitor formula is always this. Okay, represented by equation 1C. I is equal to C into dV by dt. This is nothing but the change of voltage per unit time. Okay, now let us start with the analysis. This is nothing but a inverting amplifier. Okay, but except RF, we have a CF here. So VA equal to VB, and this is our same KCL equation, what we keep writing all the time. And here this current, now this current, instead of writing in our usual way, we'll write it in our capacitor equation, what I just displayed there. So if you take this CF to the other side and if you integrate, finally you get this equation. Okay, here this value is called the time constant. This time constant is a very important property of any circuit which has a capacitor or an integrator. Okay, we'll discuss about it after some time. Just remember that this is a time constant and this is our equation. And if you want a frequency domain, just take the Laplace transform of this thing and you'll get a frequency domain equation for the same thing. And this is the formula that I have used here for converting this to this frequency domain. Okay, now if you observe in this integrator, this was an ideal case which we have discussed here. This is an ideal case. Okay, now in this there are two types of errors. One is called biasing error. What is this biasing error? I'll tell you. In this integrator, there was in this op amp there was something called as biasing currents. If you remember, in the characteristics we have discussed, due to these biasing currents, this capacitor charging, which is the main function in the integrator, will differ. The time, this time constant will differ due to some extra current this is going here, because this is not we are considering a practical case, so these currents are not zero, so the charging time will differ. Due to this there will be some error in the output. This is called biasing error. And the low frequency gain. What is the low frequency gain? See, when AC comes to the capacitor, it passes directly like this. Okay, but when DC comes, it stops here and the DC value builds up. We have also seen this in the level shifting stage of the op amp, if you remember. So the DC value keeps building up and high gain you get when the frequency is very less. So what happens is, due to this high gain, this integrator may become unstable. So we have to compensate for these two errors. So in a practical integrator, now see, this is a practical integrator circuit. This is called a compensation resistor, RC, which is nothing but this. And this compensates for the biasing, because when the currents come here, this thing bypasses the currents and the currents go to the ground. So this is called a compensation resistor. Similarly, here you have another resistor. This is a feedback resistor in parallel with CF. What this does is it bypasses the DC components, so that the buildup in the capacitor will not be very high and the gain will be stabilized. Okay, so these two simple components will stabilize your integrator circuit. This is a practical integrator. And similarly, for a practical integrator, the transfer function will look like this. Okay, this is the Laplace transform of your transfer function for a practical integrator. If you observe here, if RF is very high here in this circuit, that is, if you remove this RF very high is nothing but equivalent to open circuit. So if you remove RS, you will get back your ideal case. Okay, so this was about the integrator. Now let's come to differentiator. In a differentiator circuit, this is nothing but shifted reverse of an integrator circuit. C comes here, R comes there. Okay, so the equation will be the same. This is the minus, because here you are subtracting 0 from Vi. Okay, so this is a minus C1. Okay, and this is the same. Vi is equal to Vb is equal to 0, and here if you send RF this side, this is the final equation you will get. Okay, if you Laplace transform, you will get the S domain, that is the frequency domain, and this is the formula I have used to convert to the frequency domain. Remember, there we have used the integration formula, here we are using the differentiation formula. Okay, now similarly in the differentiator also we have the same two errors which we had there. Okay, the biasing error is same. Frequency error, in this case it will be reversed. In this case, for high frequencies, when high frequencies come, this capacitor allows the high frequencies and a high gain results in the resistor. Remember, here the resistor is like the output. Whatever comes to the resistor comes to the output. So you can say that high gain in the resistor for high frequency. Anyway, low frequencies are blocked here, so no problem with the low frequencies in the differentiator. Okay, now so again we have to use the compensation techniques to compensate for these two errors. What we are doing is, RC is the same thing, R1 parallel with RF, to have a compensation for the biasing, and CF is added in parallel with RF. So what this CF does is it bypasses the AC components, so that no problem of high gain for large frequencies. Okay, remember it just as a opposite of the integrator. Okay, and this will be your transfer function in S domain, which is nothing but the Laplace transform of your T domain. Now one more thing, here this is the time constant in case of differentiator. Remember, the time constant instead of integrator also we have discussed. Now all these time constants, whatever it may be, it should be always less than or equal to T, where T is the time period of input signal, because the system response will be slower than the input signal. So this time constant should be slow. so that the input signal is differentiated or integrated, whatever it is, properly. If the time constant is very high, then the input signal is not reproduced faithfully. So this was about these applications. In the next class we'll be discussing about comparator.